The next element is the object. So here we have our yellow school bus. And how can this object be objectively quantified? So there, first we have to understand how color is generated altogether. So if we have colored object, either opaque, that means it doesn't, light isn't can't get through it, or transparent here. This light, the light is falling onto the object, and then the object is selectively absorbing the light. So some light beams are kind of stuck into the material. They won't be reflected here, or they won't go through the sample here. And then in the first example here, the light is reflected. So in another, I have white light going in, then the red part is absorbed and the blue part is reflected. Or in the transparent model here, the white light is partly absorbed, the red parts or yellow parts, and the green part of the light is going through. So that's transmitted then. So it's always selectively for some wavelength what's happening here. So I'm going a little bit more into this color reflection here. So I have the incident light, which is consisting of all colors, which is symbolized here by all colors. Then the light beams are going a little bit into the object, and some of them are absorbed and some of them are reflected. And we have two kinds of reflection. One is the diffuse reflection, so that's going into all directions here. And normally we also have a part of a directed reflections, and that's like mirroring here, though that's the glass actually. And you see the blue parts are missing in the directed reflection, so not every color is reflected, and that gives the effect that we see this surface as yellow. And what is now happening when we are doing color measurement? We have some kind of a real light source, which we try to have as perfect white as possible. And this light is falling onto the sample and then reflected by the sample, for example. And then we have a function of splitting this light. So this could be done by a prism as we saw it beforehand, but normally that is a grid, a holographic grid. And then we can see all the colors still in that light here. And then for each color, the proportion of the reflected light is measured here, and thus we get a spectral curve. For example, this yellow sample will certainly not reflect a lot of blue light, and then we get a spectral curve, and that might look like this here for the school bus yellow. We have a very low portion of the blue light here, and then it goes up a little bit. Green is in there. Of course, there's yellow and even a big red part, as it is a rather reddish yellow. And that is a really special spectral curve for this yellow. So that is unique, and that's objective as well. As we can say, it's always a percentage of the light that we sent onto the surface. So we had a light coming in by 100%, and then the reflected light of the blue part is only very low, and the reflected portion of the red light is very high here. I remember you to interrupt me if you have any questions. If you're not saying anything, I think you're okay. So just as an example here, for 600 nanometers, we have a reflection of 53%, and that gives that curve here. So the sensor is telling me 53% are reflected. So actually, we are already done for the object here. We have the object, and instead of the object, which I see by the eye, I use that it's now quantified by the spectral reflection or transmission curve. Of course, that's true for transmission as well.